So the next section I want us to talk about is section 8.1. Now I know we're jumping from section 4.1 to 8.1, but 8.1 is the only section we cover in chapter 8, and it fits really well in chapter 4, and it was really, really lonely. So I'm glad we moved it ahead a little bit. So section 8.1 is all about systems of linear equations. So a system of linear equations is when I'm given two equations in standard form, right, ax plus by equals c, or they could be in y-intercept form. Typically, they're given to us, though, in standard form. If I'm given any two such equations, this is a linear system. There are three different solutions to a system of linear equations. So first off, when I have a system of linear equations, I want the solution to be true for both of those equations. So if my two lines intersect, then they're going to have exactly one solution. If my two lines are parallel, meaning they have the exact same slope, that means there's going to be no solutions. And if my two lines are the exact same line, for example, y equals 4 and y equals 8 halves, okay, those two lines would be the same line, and this system has infinitely many solutions. Specifically, all the points on this line would be the solution to that system of equations. So there are three different ways that we're going to talk about solving systems of linear equations. Here's some terminology real quick for us, though. So if two graphs intersect at a single point because it has a solution, we say that's consistent. A set is consistent if it has a solution. Because the equations are not the same equation, they're independent of each other, we say that they're independent. If we have parallel lines, those are inconsistent because there's no solution, right? They don't intersect at all. But those equations are still not equivalent, so they are independent. And then if two graphs are the same line, that's consistent because it has a solution. But those equations do depend on each other because they're the same, right? You depend on yourself. So we'd say those were dependent. The first thing we can do is to solve a system of equations by graphing two lines. So if I have x plus 2y equals 2 and x minus 2y equals 6, I can find the solution to this system of equations by graphing. So what do? I graph the first equation. On the same plane, I graph the second equation, and then I determine the solution, and I can check my solution by plugging the ordered pair that I find back into both equations. So why don't I go ahead and we're going to graph these two equations. So I want to go ahead and graph these two lines on the same coordinate plane. In order to do that, I need to get both of these equations into slope-intercept form so that I know how to graph them. So with the equation on the left, I'm going to take away x from both sides. So I get 2y equals negative x plus 2. I divide both sides by 2 to get y all by itself. So I have negative 1/2 x plus 1. Next, I have x minus 2y equals 6. So I'm going to take away x from both sides. So I get negative 2y equals negative x plus 6. I divide both sides by negative 2. I get y equals 1/2 x minus 3. Then I can go ahead and graph these lines. So let's get some more colors involved. My first line is when y equals negative 1/2 x plus 1. So 1 is my y-intercept, and negative 1/2 is my slope. So my slope, remember, slope is rise over run. So this has a negative slope. It's going to look like it's going downhill. So that means I go down 1 over 2, down 1 over 2. Remember, you only have to plot 2 points, but I like doing a little bit more in order to graph our line. Now in orange, we're going to graph y equals 1/2 x minus 3. Negative 3 is my y-intercept. My slope this time is a positive 1/2. That means my graph is going to look like it's going uphill. So I go up 1 over 2, up 1 over 2. And it looks like these two lines intersect and have one solution, so it's a consistent system at when x is 4, y is 1. So let's go ahead and plug that in to both of our equations to see if we got the answer correct. So if I have 4 plus 2 times 1, sorry, that's a negative 1. So 4 plus 2 times negative 1 equals 2. I get 2 equals 2, which is true. If I have 4 minus 2 times negative 1 equals 6, that's going to give me 4 plus 2 equals 6, so 6 equals 6, which is also true. Note, if this point had not been true in both of my equations, I would have made a mistake and I would have needed to go check my answer. Now, graphing systems of equations is great. The issue is sometimes our two lines don't always intersect at a nice point like 4, negative 1/2, right? They could intersect at a point like 3/8, negative 4/5, right? That would be really hard to see from looking at a graph. So we have two other methods of solving systems of equations that would allow us to find this intersection point. One of those ways is by substitution. So what you're going to do when you solve a system of equations by substitution is you get one of your variables by itself. So I'm going to take one of these terms and solve it for a given variable. Then what I do is I substitute it back in to my second equation and solve. We'll then find a value, we'll then have an equation in one variable that I can solve, and then we can use that value to find the other variable's value. Let me work this through. So I'm going to take x minus 2y equals negative 3, and I'm going to go ahead and solve that for x. Why did I pick x? Well, it was already all by itself. It was the easiest thing to solve for. So I have x equals 2y minus 3. That's my step 1. Step 2 is to substitute that expression into the other equation. So I'm going to take 5x minus 4y equals 9, and instead of having 5x, I'm going to have 5 times 2y minus 3 minus 4y equals 9. So I get 10y minus 15 minus 4y equals 9. I add 15 to both sides, and I run out of space because of course I do. So I have 6y equals 9 plus 15, which is 24. We divide both sides by 6. I get y equals 4. Awesome. I now have one of my y. I now have one of my variables solved for. I can then substitute this into either of the equations that are left. So I could substitute it into 5x minus 4y equals 9, or x minus 2y equals negative 3. It doesn't matter. I'm going to plug it back into my first equation. So I have x minus 2y equals negative 3. That means x minus 2y, oh, this is step 3, FYI. X minus 2 times 4 equals negative 3. X minus 8 equals negative 3. I add 8 to both sides, so I get that x equals 5. So where these two lines intersect is the ordered pair. Be sure to write it as an ordered pair when x is 5, y is 4. And we could check our solution by plugging it into either of our equations. Well, we would check it by plugging it into both equations. So let's solve a couple more. I have y plus 1 equals 5x plus 1, and y equals 5x minus 1. So let's go ahead and solve this. I already have solved for one variable, so that's a good step 1. I can then plug that in to y plus 1 equals, let's go distribute that, 5x plus 5. So we're going to plug in 5x minus 1. So I have 5x minus 1 plus 1 equals 5x plus 5. That means I have 5x equals 5x plus 5. I can take away 5x from both sides. So I get 0 equals 5. Is this a true statement? No. So this means our equations have no solutions, right? If you get a false statement, there's no solutions. The same way, if you get an always true statement, that means you have infinitely many solutions. So let's take a look at this second set of equations. Here's my step 1. Y equals 3 minus 2x. I'm going to plug that into my second equation. So I have 4x plus 2 times 3 minus 2x equals 6. That gives me 4x plus 6 minus 4x equals 6. I'm left with 6 equals 6. That means that these two lines are the same, and so there are infinitely many solutions. That means these two lines are right on top of each other. The third method I want us to talk about is the elimination method. So let's take a look at 3x minus 4y equals 11, And negative 3x plus 2y equals negative 7. If we added these two equations together, the x term would be eliminated. So let's go ahead and add them together and solve for y. So 2 3x's would cancel. I'm adding these together. Negative 4y plus 2y would give me negative 2y. 11 minus 7 would give me a positive 4. So I get y equals negative 2. Now that I have that y equals negative 2, I can substitute back into either equation and solve for x. So I have negative 3x plus 2 times negative 2 equals negative 7. Negative 3x equals negative plus 4 equals negative 7. If I go ahead and, minus 4, so plus a negative 4. If I add 4 to both sides, I have negative 3x equals negative 3. So I find that x equals negative 1. And I have found where these two lines intersect is at the point when x is negative 1, y is negative 2. The key to using this method is to obtain for one of my variables coefficients that are additive opposites. Additive opposites, when you add them together, equal 0. So how are we going to go through the steps to solve these equations? So the first thing we want to do is we need to get both equations in standard form. Okay? Then we can transform either the equations as needed by multiplying both sides by a constant, either negative or positive, so that two of our variable terms have coefficients who are additive opposites. We then will go ahead and add those two equations, and I can solve what remains for one of our variables, either x or y. I can then use that to find the other value we need, either x or y, by substituting into our original equation. Always try to make sure you substitute it back into your original equation in case you made a tiny mathematical error. And then you can check your values in both original equations. So if I have x plus y equals 5 and x minus y equals 6, I can see that my leading coefficients on y are opposites, so they're going to cancel out if I was to add these two equations together. X and x gives me 2x, my y's cancel. 5 and 6 gives me 11, so I have x equals 11 halves. This will allow me to solve for y. So I have x minus y equals 6, so I have 11 halves minus y equals 6. But let's write 6 as a fraction with a denominator of 2, so that'd be 12 halves. I can subtract 11 halves from both sides. I get negative y equals 1 half, so y equals negative 1 half. So these two lines intersect when x is 11 halves and y is negative 1 half. Next, I have 3x minus y equals 11 and 2x plus 5y equals 13. And I have to decide, okay, which variable do I want to eliminate? Well, let's focus on y. And I'm going to multiply this first equation by 5 on both sides. So that gives me 15x minus 5y equals 55. If I go ahead and add these together, I get that 17x, and my y's cancel, equals 68. Well, when I take 68 divided by 17, I get that x equals 4. I now have solved for x. So I can plug that into either of my equations. It doesn't matter. I picked the top one. And see what my y value is. So I have 3 times 4 minus y equals 11. So 12 minus y equals 11. I subtract 12 from both sides. Negative y equals negative 1, so y equals 1. So our point of intersection is when x is 1 and y is 4. And we could have seen this pretty easily by graphing, but this first example we really couldn't have. I also really like elimination. It seems like a little less messy to me when we're substituting in. It's often that we cannot distribute properly or add our constants and variables, coefficients well, and have more mathematical errors. So elimination is definitely my fave. We can also use systems of linear equations to solve word problems. So, the National Football League and National Basketball Association seasons from 2015 to 2018, it would cost you $241.84 to get 2 football tickets and 1 basketball ticket. it would also cost you, one football ticket and two basketball tickets would have cost $204.74. I like this word problem because it basically just gives you your system of equations. I have that two football tickets and one basketball ticket is $241.84. And I have that one football ticket and two basketball tickets is $204.74. I want to go ahead and solve this by elimination. Let's pick f to be our focus variable. So I can multiply this equation right here by -2, and I would get -2f minus 4b equals -409.48. I want to add that to my original equation. These cancels out, and I get that -3b equals -167.64. I divide both sides by -3. I get that b equals 55.88. So $55.88 was the average price of a basketball ticket. I can solve this. I can now solve for the price of a football ticket by substituting 55.88 back into my original equation. And I just picked the first one, but you could have picked the second one. Either way, it would give you the same answer. So I have 2f plus 55.88 is 241.84. I subtract 55.88 from both sides. I get that 2f equals 185.96. I divide both sides by 2. I get that the average football ticket cost $92.98. So now I know the average ticket prices for two sports.